Yeah. Okay, so we're just about ready to start. But before we do get, we're not quite ready here anyway. Are we?
It's still coming up.
Yeah, it's still coming. So I was thinking, suppose you each send me an email about your proposed topic for the project. Okay, and then we can iterate back and forth. And if you're not sure what you want to do, just why don't you put that in the message. But each of you send me a message about what you're thinking of as a project, or what field you'd like to do something in, and you want some feedback from me, or whatever you want. Okay, so you can talk to me in the hall afterwards. But anyway, I was thinking this would get you started, because I definitely want you each to have a project identified before the break, and some feedback from me on how you might get started. You know, who's an expert in the field, or where would you find an article or two on this particular topic? You know, but actually, getting started in science, sometimes a name and an email address is really useful. So to help you go through the literature, I mean, you can do a literature search, and we often do literature searches, right? But sometimes someone can tell you that there is some particularly good articles on the topic, either good because they explain it very well, or they have the latest results, or some other thing like that. So do send me a message, and if you want, just get me before or after class. And okay. Any issues on homeworks? Huh? No, I think there's going to be an occasional homework. Yeah, but you're mostly over the hump, but not quite there yet. Some people have volunteered to give homework problems, and I still have another lecture or two. I am still thinking about the holography. You know, that I could show you those, but the lecture after next isn't set yet. I'm trying to get one on X-ray scattering, which we don't have, and it's just not settled yet. So next lecture, I'll let you know what's up. Okay, we all set? Did you? Is it? Do you have? Yeah, everything's set. Okay, so the speaker today is Tony Van Buren from Lawrence Livermore National Lab, and also from UC Merced, and he's going to speak on the use of NEXAFS in material science. So,
thank you. Well, thanks. Oh, okay. Well, thank you. Good. So the title, as you know, has changed from the original title that was probably in the syllabus. And when David approached me about talking to you, I heard that the group was really interested in material science applications of various synchrotron radiation techniques. So rather than try and cram everything into one, I thought I'd explain the NEXAFS technique and give a number of examples on various applications that are fairly unique to the NEXAFS field. And then I actually went online and saw that Anders, who was before me, had actually covered a fair bit of this. So there'll be a little bit of overlap, but I think there's going to be a number of applications that are fairly unique that are specific to these element-specific probes. So the outline of my talk is as follows. I'll give you just an overview of the X-ray absorption process, and then I'm going to talk about how do you measure NEXAFS or XANES. There's a number of different acronyms for this near edge, as we'll get into, but I'm going to pick out the 4 real salient points about these techniques. 1, that it's element specific, and 2, it measures the partial density of empty states. So you're actually getting the electronic structure out of this. And 3, it's sensitive to the local bonding, the bonding of the atom that's absorbing the photon. And 4, with synchrotron sources, there's all sorts of really quite interesting polarization studies that you can look at and actually get information about order and geometry on materials. So then I'll follow by a number of different applications.
I must have, I didn't turn it on.
Oh.
There's 2 switches.
Okay. in this field, there's really two big starting points where the NEXAFS spectroscopy started. And one is in surface chemistry, in particular looking at catalysis. There's a wealth of information looking at how catalysts can be probed using NEXAFS spectroscopy. And this is in particular catalysts of molecules bonding on surfaces, where you can get information of molecules' order and how they stand up and how they bond to the surface, and actually how the catalytic properties happen in real time. The next is like what I'm calling environmental chemistry. And what I mean by environmental chemistry is basically from the NEXAFS you can get information about the oxidation states that are of the elements that you're interested in. So you can see, well, okay, as a reaction or something's happening on a surface, does it go from the +3 to the +4 oxidation state, or what's actually happening on the surface? So then I've given 4 examples where I've taken stuff from research that my group at Lawrence Livermore is actually quite interested in. In particular, the electronic structure of quantum dots, and how self-assembled monolayers order on surfaces, and how you can switch surfaces using self-assembled monolayers. Then I've shown an example of chemical mapping and imaging technique that you can actually get images of surfaces, both electronic structure and chemical information. And then I'll give you a flavor for magnetic effects in X-ray absorption spectroscopy. Now, I know later in the term, I think 2 lectures from now, you're going to have one of the world leaders give a lecture on this, so I'll just give a flavor for that and leave the rest for Joe Storr. So as you may know, in the X-ray absorption process, you're actually probing the empty states. And what you do is you scan the photon energy until you kick an electron from a core level up into the empty states. Now, when we say NEXAFS or XANES, or actually what I just use is XAFS, there's a number of different acronyms, and they basically mean the same. So XANES, X-ray absorption near edge structure, and NEXAFS, near edge X-ray absorption fine structure, are basically the equivalent. And that is usually the first 50 eV above the onset of the absorption edge. And the absorption edges, which I'm showing here. Now, traditionally, these terms have been used interchangeably, but I guess in reality, NEXAFS usually means light elements, so carbon, oxygen, nitrogen. It's interesting to note that both of these processes need a core hole to start. And in this case, the X-ray generates the core hole. But you can generate the core hole with an electron beam also. You can do similar experiments in a TEM where you generate the core hole with an electron beam, and again, an electron falls down from the upper levels, and you can map out the empty states in that manner. So again, the XANES is dominated by the equation that I've shown at the top of the page here. This is the Fermi's golden rule, and that gives the probability of transitioning from your initial state to your final state. So the first term with the Hamiltonian here shows the final state and the initial state. So when you do the dipole approximation, you actually get selection rules that come out of solving this equation when you put in the wave function. And that says if you start from a core level that's an S-like level, you can only go to angular momentum states that are plus or minus 1. So from S, you can go to P, as I've shown here. In this box here, the 1s state is called the K-edge. Okay, so now if you go to the next orbital, the orbitals 2, you can have excitations from the 2s, the 2p3½ and the 2p1². The p levels are actually spin orbit split. And these are transitions in the 2s, again, from the K to P, but from the 2p3½ and the 2p1² is actually from P to either S and D states. And so on. From D, you can go P and D. And you can actually get quadrupole transitions, like that's for L plus or minus 2, but those are very, very weak. So here you can see that the technique is 1, element specific, because you're starting with a core hole, and the core hole is localized to that atom. And number 2, these are angular momentum resolved densities of states, because there's a selection rule associated with the transition. So So I just want to show you, if you're actually taking an experiment, what is this, or actually taking a measurement, what does the process look like? So this is the zinc K-edge X-ray absorption. And this is at around 9.5 kilovolts. So you start scanning your photon energy, and you have the pre-edge region. This pre-edge region can be just flat, but you can have other transitions, excitations that are lower. So you could have a background there, especially if you're doing these things in electron yield. So it's composed of absorption edge tails that are further or lower down in energy. Then as we come to the absorption edge, and this is called the XANES, or the near edge structure. And this actually maps out the densities of states, of the empty states in the conduction band for a semiconductor, or above the Fermi level for a metal, or for molecules, it's basically probing the LUMO, the lowest unoccupied molecular orbitals. So this composes information of oxidation state, and actually can give you chemical information because of the bonding. Now, if we continue our scan in the right direction, we go into what's called the extended X-ray absorption fine structure, the XAFS region. Now, I'm just going to touch on this briefly today. Now, the XAFS, you can see, extend up, can be in some cases up 1,000 eV above the absorption edge. Now, these oscillations are independent of the electronic structure, and what's actually happening is the ejected electron interacts with nearest neighbor atoms, and you get constructive and destructive interference because the wave function bounces off the electron and interacts. So you can see that because you're interacting with the nearest neighbor, you're going to get nearest neighbor information. And the XAFS technique is one of the largest characterizations field that uses this X-ray absorption spectroscopy because it gives you unique information. It gives you bonding and bond order and also chemical information. Now, the thing about the XAFS is just by looking at it, as the data comes out, it's hard to interpret what's actually going on here. Whereas the near edge, you can actually look at it and immediately get relevant material science information. So what you would do to get information is, let's say you have your atom in the middle, and it's absorbed an X-ray. And you've ejected your photoelectrons. The photoelectrons disperse, and they can interact with the nearest neighbors. Interference is provided, and you get oscillations in your X-ray absorption structure.
I don't know how hard people on the internet may not be able to follow you pointing there, but they could follow your mouse. But you don't have one.
Actually. No.
Claw. Okay, sorry. Stick with it.
All right, so what you now do to actually get the information is you would take your absorption edge, and then you will subtract the pre-edge and post-edge backgrounds. So you take a subtraction, and then you take the Fourier transform of that, and that's going to give you your radial distribution function in real space. This was first realized by Sayer et al. And Farrell Lytle at Stanford. And here I've shown one of the first examples, and it's for polycrystalline and amorphous germanium. So on the solid line, you can see that both the dotted, and which represents the amorphous, and the solid line have a fairly clear peak, because your amorphous germanium has at least nearest neighbor information. And obviously the solid material has nearest neighbor information. But as you go to next nearest neighbors, you still see clear peaks for the crystalline structure, but the amorphous structure is all washed out, basically showing the amorphous germanium doesn't have long range order.
So what's kind of the maximum distance away that you can get useful information on?
That is fairly materials dependent on the quality of material, but usually you can get 4 or 5 shells.
just wondering why the interference of the electron wave function can affect the X-ray absorption.
Well, the X-ray absorption process has already happened. This is the interaction with the nearest neighbor wave functions. There's, I think, some slides at the back of this talk that I think address that particular question. So now, how do you record X-ray absorption? So there's a number of different modes. I've shown the top mode is in transmission. Basically, you shine X-rays on your sample, and the X-rays become attenuated as you go through your sample, and you can see the ratio of your incoming X-rays to your outcoming X-rays are proportional to the exponential of the absorption coefficient times the thickness. So when you do it in transmission, you can see in the plot beside the transmission curve, you scan along and you get a dip in your material because the material is now absorbing. So it's an inverse of what you normally see in the NEXAFS spectra. Excuse me. Well, the nice thing about doing things in transmission is you actually can get the true absorption coefficient out, because these measurements are a true measure of the absorption coefficient. And it's a fairly bulk-sensitive technique because you're going through the whole sample. The drawback of some of the transmission experiments is you actually need fairly thin samples depending on what your X-ray energy and what edges you're after to penetrate through to get reasonable signal. A more common way of looking at the near-edge structure is electron yield. In this case, you shine incidence X-rays on your sample, and you create a core hole, as in the diagram in the bottom corner of the plot. So you form a core hole, and then an electron from a higher level falls down. You get an Auger electron ejected. The Auger electron can interact as it goes out with valence electrons, and you get a cascade of electrons coming out. So you actually get a whole bunch of secondary electrons, which is shown in the plot in the middle. And all you have to do is have an electron counter, a channeltron, or a channel plate, and you can count the number of electrons that are coming off, and that's proportional to the original core hole was there. So it's proportional to the absorption coefficient. So the nice thing here is that, well, the nice thing here is a fairly simple measurement, because either you're counting electrons, or even simpler is you just attach a current, a wire to your sample, and you measure the drain current coming off your sample, and you can measure electron yield. It's a very simple setup. The issues with this, and some like it, I like it because you can now tune your samples to be quite surface sensitive because you're dealing with electrons rather than photons. Another method that I haven't shown here, but it's very similar to the electron yield, is instead of looking at the Auger electrons, the core hole can decay and you get a fluorescence photon given off. This is fluorescence yield X-ray absorption. By counting the total fluorescence yield photons, you can get, again, a map of the absorption coefficient, and you can map out the X-ray absorption. But again, here now it's bulk sensitive. You're probing down to 1/10 of a micron, in some cases a micron. So by doing different techniques, you can make these techniques surface sensitive or bulk sensitive, and they're element specific. So the one key that I just mentioned there is NEXAFS measurements are element specific. So here's a wedge sample that has copper, iron, and nickel. And it's taken at 3 different regimes. So if we go from the top to the bottom, so the top, you can see that you have a fairly strong, in red, iron signal because the iron layer is quite thick. The copper layer is the same thickness the whole way through, so you can see in the 3 plots along the wedge, it's the same intensity. And then you can see that the nickel signal, because this is done in electron yield, is actually changing, even though the nickel layer is not changing in thickness. But what's going on here is the ejected photoelectrons can't get out. So basically, you start attenuating your nickel signal. So this is really nice because you can actually, from your wedge sample, you can strip off the layers one by one. Now, another thing to note here is the actual intensity, or how large these peaks are, scale with the number of empty states that the electron can transition into. So we see for iron has the most empty d electrons, and we see that that peak actually is the strongest. Whereas copper, you see it's actually quite weak. It doesn't have those very sharp D lines, sometimes called the white lines. And that's because copper is D10. There's no real empty D electrons to go into.
So then how do you see a signal at all then?
Oh, because this is from a P level, right? So there is some S contribution there. And as it turns out, copper is not really D10. It's D9 point something, depending on whether you have a surface layer or whatnot. So there is a small D contribution still in the empty states. So I chose this example because we've talked about how the NEXAFS are actually mapping out the densities of states, or the partial densities of states of the conduction band, or whatever empty states you're looking at. So what I'm showing here is a determination of bonding and the bond order. And I'm showing two examples of a cubic boron nitride and a hexagonal boron nitride. And the cubic boron nitride is sp3 bonded, and the hexagonal boron nitride is sp2 bonded. So this is the top curve and the bottom curve. So just by looking at the bonding coordination, you can see that the absorption edges of these two materials are completely different. But there's one more thing going on here, is that in some cases, the ejected electron can still see the core hole. And these are called final state effects, that it forms like a bound level. So the very sharp, what's called pi star, if you work in NEXAFS field a lot, you're going to hear pi star, especially with carbon and boron nitride. This is a resonance feature, akin to an excitonic feature. So you actually get a feature that's associated with the final state of the system, not the initial state of the system. So you can map out things like excitonic features using the X-ray absorption technique, as well as getting information on bonding. So one of the other interesting things and uses for XANES NEXAFS is it's a high flux, and at synchrotrons you can get very well polarized light, linearly polarized or circularly polarized. In this case, we're interested in linearly polarized light. And what you can do is you bring your X-ray in, and it has an electric field vector. Now, I want to be a little bit careful here, because I realized this after the fact, that depending on whether you have a sigma bond in a linear molecule, or if you have pi star features in the text, they call this plane molecules. And there's three slides at the end of the talk where this describes it in complete detail, which I didn't put in the presentation per se. But what happens is if in a plane molecule where you have pi bonding, if the electric field and the transition dipole matrix align, you get a maximum in the blue curve. If they're orthogonal to one another, you get a minimum. Now that's different if you have sigmas, it's opposite. So my first example is in the field of catalysis. And what I'm showing you here is a tin oxide aerogel. I'm not sure how many people know what aerogels are, but to first approximation, an aerogel is solid smoke. The densities are 1%, less than 10% down to 1% of the full density. You can hold them up, and they're transparent in some cases. And what I've shown you here is a tin oxide aerogel, which is an attractive material for gas sensors. And it's made as prepared, the 20-degree sample. And then we anneal it. There's your TM pictures on the left-hand side, my left. And then you can see at 250, there's not that much change. At 400, you can sort of see the structure is beginning to change. And at 500, all the same length scales, there's a complete change in the size of the particle. And what we've now done is we've looked at the NEXAFS as a function of this. And we see that the near-edge structure is changing completely as we do our annealing. It turns out that at 20 degrees, the structure is akin to SNO, and it's amorphous. And if we map our amorphous SNO, it matches ideally with what we see at 20. But as soon as we start annealing, what happens, the material starts to crystallize and actually converts to SNO2. So here, just by annealing, we're actually changing the electronic structure of our aerogel. And this is actually very useful for catalytic purposes. The next thing that's of interest in these materials is you can actually get surface chemistry or chemical information from your NEXAFS. And what I've shown here is for a polymer system. And the first two plots, we see that if we have a carbon, this is a carbon X-ray absorption edge, and we see if we have a polystyrene and a polyethylene, you can see that if you have a carbon bonded to oxygen or carbon bonded to hydrogen, these edges shift. And again, if you have a double bond, you have now pi star features. The pi star features show, again, you get these sharp features in the near edge. And then if you have sp2 bonded, which you see in the polystyrene and the polyamide, you get a peak again at lower energies. That's related to the pi star exciton, this time in carbon. But the nice thing about this is you get a fingerprint for each material. So if you're searching for a particular material, you can compare it to these fingerprints and actually separate out structures. But another nice thing is you can do chemical mapping. So what I've shown here is a combination of two polymers, polystyrene and polymethyl methacrylate. And what I've shown here is in plot A is the contrast in the polymer blend as a function of excitation energy. This is work done in a group of Adam Hitchcock. So we've got the red plot on the bottom, absorption, is the polystyrene, and the green plot is the polymethyl methacrylate. And we can see that when we excite at 283, we get basically a homogeneous sample, because in that regime, the two absorption edges look the same. And then if we go up to 285.1, that's a large red peak, you can see that you get immediate contrast between the two types of polymers. And then if you excite up at 288, where you're actually on the green line, you can see that the contrast is reversed. And then as you climb up, you start losing contrast. So this is a nice way where if you've got polymer blends that have different absorption edges, you can look at your sample and actually see segregation in these materials as a function of processing. And there's a nice plot in section E that's color that shows you exactly how these materials separate. So I've taken this actually from the Stanford website and basically given you an example of environmental chemistry that can be done here. Background to this slide is the Rocky Flats nuclear site had an area where they were storing radioactive waste in drums. And the radioactive waste was stored in drums, and it was stored basically on the ground. And the drums began to leak. What they did is actually put down cement to try and contain the plutonium leaking, because you got a plume of this material leaking through the ground. Now the problem is that they didn't really know what species of plutonium, because there's numerous oxidation states of this material, was actually segregating through the material. So if you don't really know the oxidation state, you don't really know what kind of remediation methods you can do to try and stop it. So what they've done here, this is a group from Los Alamos, and if you want more information, it's on the Stanford website. And here is actually the people at Rocky Flats cleaning up the site. We've looked at 3 different oxidation states of plutonium, 3+, 4+, and 5, and you can see that the edges are all shifted to different energy. But what I've shown here is the soil sample, this Rocky Flats soil and concrete. You can all see that it's plutonium 4 state here. So this gives you information that you know what kind of chemistry that you'd need to do to try and stop these type of plumes or counteract such things. Yes?
So here it appears that as you go up in oxidation state that you move higher in energy. Is that a general?
Okay, so in general terms, yes, but you have to be a bit careful with absorption edges, because usually at the onset you can have both the densities of states effect and you can have a final state effect. So the final state effect can cause differences in different oxidation states. Another thing that you touched on before is if you have a level that's D10 and you go to an oxidation state, let's say that's now D9, you can all of a sudden light up a white line. So you can have significant changes in your absorption edge. So work that's being done at my group at Lawrence Livermore is we're looking at various types of self-assembled monolayers. And I'm not sure how much the group here knows about self-assembled monolayers. If we look at the diagram in the bottom corner, this is a self-assembled monolayer system, and it consists of, at the bottom, a sulfur group. And the sulfur group is usually bonded to a metal, in most cases gold. And then you can see that you have a fairly long alkyl chain, and at the top you can have a head group that has a different type of chemistry. And this is your typical alkane thiol self-assembled monolayer. And the interesting thing is, on the top plot, is if you put your gold substrate in a solution of these materials, what's going to happen is over time these materials bond to the surface, and they bond and they lay flat originally. But as it turns out, the van der Waals interaction is such that it will cause these alkane thiol groups to repel one another. Yet the activation energy for the thiol to bond to the gold is such that it's more energetically favorable for these materials to stand up, so they actually self-assemble in real time. So if you wait for some period of time, depending on preparation conditions, these things will all stand up. So the thing that you'd like to know here is, okay, well, how do they stand up? And are they angled? And what degree is the order? And what's the head group doing? And how stable are they, etc. All things that aren't necessarily really straightforward to get at with other techniques. There's actually a numerous, what I'm going to call hot applications for these type of materials. There's been a recent paper that shows you can actually get switchable self-assembled monolayers where they stand up and they are hydrophilic, and then if you remove one of the groups, they'll actually bend over and you'll get a hydrophobic surface. So you can switch it from a water-loving to a water-repelling surface, and with just changing a little bit of surface chemistry. Another one of the big uses here is actually you can use these as templates for attaching proteins to surfaces. And this is obviously very interesting from an aspect if you want to make a biological sensor or a chemical sensor, or just have a system where you can change the surface chemistry of a material and have it active for a certain protein or whatnot. And the third example that I'm showing here over on the right is these interlocking molecules. These molecules are called catenanes. And to first approximation, these are two rings that are free to rotate with one another. So they're completely separate. But these rings, you can actually get them to lock into conformation sites so they can switch. So these are molecular switches. So there's been work, our group has done some work on actually using thiol chemistry to bond these things to surfaces. But you'd actually like to know what the conformation of these rings are with respect to one another. So I'm going to show you some of the information you can get by using the polarization-dependent aspect of the near-edge structure. What I've shown here is an X-ray coming into a self-assembled monolayer. In this case, oh, I didn't show it on this one. Actually, the diagram of the self-assembled monolayer is on the next page. It's coming in at 20 degrees, and this self-assembled monolayer has a carboxylic acid group sticking on the top. And the sharp peak here is actually the carbon double bond oxygen feature. So now we see if we change the angle of our sample in our X-ray beam, we see that these actually features change in real time. The polarization dependence changes these around, and the bottom graph is actually the different spectra between the two. So from taking this information and the different spectra, you can actually get, number one, if it shows this type of polarization, these films are usually ordered. Number two, you can actually get the tilt angle from these materials. And by looking at what the carboxylic acid group is doing, you can actually see the head group, what its orientation is doing. And we found that we can actually rotate the head group in real time by just changing the pH of our solution. So what these things actually look like, they're actually sitting on the surface, and the self-assembled monolayers are at 42 degrees from the surface normal. And depending, if you actually create it with an acetic acid, these things are actually standing up. If you create them in ethanol, they actually sit flat. So this, again, is like making hydrophilic, hydrophobic surfaces. And this is really great. This is really powerful techniques showing what molecules attach to surfaces and how you can actually feed back to the synthetic protocol and change things in real time. Now, I showed one with an alkyl chain. I won't spend much time here. This is a self-assembled monolayer that has a benzyl group and an alcohol sticking out the side. And again, you see the same sort of polarization dependence. And in this case, we're looking at where we put this carboxylic group on the sample. And if you have it all the way over in the 2 position, it actually interacts with the surface and sucks down. And if it's over in the 3 position, these materials stand up, and in the 4 position, these materials stand up. So again, yes? Again, what we're getting here is we're getting orientation. We're seeing how the head groups are moving depending on preparation condition, and we're getting order in our materials. Yeah.
Okay, so on the previous slide, you said, or a couple slides back, that these are relatively stable. Okay, so you're doing these measurements in ultra-high vacuum. Does that affect how long you can do these things? You're under a beam irradiation.
Very good question. Excellent question. So usually, if you have a very high flux that you'd have, let's say, from an undulator beamline, it wouldn't be very good for most self-assembled monolayers. They would break down. We do almost all this work at bend magnets where the flux is down. Of course, in some cases, you can get around this by just closing slits down, but we found that for a lot of these self-assembled monolayers and these biological samples, in this case, less flux is better. The other thing to note here is that the thiol gold bond is fairly strong. This is the basis of some of your catalytic converters. So you have a platinum catalytic converter. Sulfur from your gas is actually getting trapped on these things. That's how bad gas gums up your catalytic converters. All right, so another field that we do a lot in my group at Livermore is to look at electronic structure of quantum dots. I'm quite sure everybody here is, yeah, you guys are probably more expert on these type of quantum dots than I am. So what I'm showing here is, again, cadmium selenide quantum dots. All the way over on the left-hand side is we show the optical absorption and the photoluminescence. And as we know that as we change the size of our quantum dots, we can get it to emit different colors. So it has really nice applications for various photovoltaic tagging techniques, etc. Now the key here in quantum confinement is what I show all the way over on the right, is that you'd expect the band gap to open up. The conduction band shifts up and the valence band shifts down. So you say, okay, well, why do we need a synchrotron? Well, as it turns out, other nanocrystalline systems aren't necessarily characterized as well. And you find out that if you're just doing PL, and you don't know where it's coming from, you don't have any element specificity, you get really lost fast. So in some cases, the byproduct can have the PL, or the supernate can have the PL, or the PL is coming from the surface, or it has nothing to do with quantum confinement. So in here, when you have a very well characterized system, it's great, and there's been a lot of work done to prove that what's going on in both the cadmium sulfide and the cadmium selenide. But if you don't have, let's say you're working on a research system, it is very dangerous just to go on PL by itself. So our group is actually mostly interested in group 4 nanomaterials, silicon and germanium. And we grow these out of the gas phase, so we have an evaporator. And we evaporate material into the gas phase. There's a buffer gas. You get a supersaturation. It condenses, much like raindrops condense in a cloud, and you can put them on a substrate. And we do various techniques of proving that the crystallinity and size, AFM, and we get reasonable size distributions out. So the first system that we're interested in here is we've got a very dilute system on a substrate. We have quite under sub-monolayer coverage. And if you have techniques that aren't element specific, it's very difficult to extrapolate electronic structure from substrate from the material that you're most interested in. So here, on the right, I show the absorption edge of bulk silicon done in total fluorescence yield mode, and 2 nanometer clusters and 1.6 nanometer clusters, and you can see that the conduction band edge is moving to higher values. And again, using soft X-ray emission, we do it also for the valence band. You see the valence band is opening up. Both of these techniques are element specific, so you know that this is actually coming from the silicon. And from the X-ray absorption techniques, you can tell the difference between silicon oxide and silicon nitride and silicon metal. So you can actually tune to the silicon, and you can prove to yourself that, OK, this is an effect of the silicon quantum dot, nothing else. So the nice thing about this is you can see shifts in the conduction band as you're moving to higher energy and shifts in the valence band. Together with this, you can actually get a band gap of these structures that's element specific. So here we get the band gap of, as a function of particle size in our systems. So we get clear trends, as you'd expect, as a function of quantum confinement. The interesting thing here is we get independent measurements of conduction band and valence band shift. Now, why is that important? Well, if you want to make contact to a material like this, if you want to know a device, if you want to inject electrons in, you better know how these band edges are moving as a function of size. It's common sense. It's something that just can't come out of the straight PL measurements. And then we can play some tricks. Well, if we can make this for silicon, we can also make it for germanium. And the interesting thing here is that at room temperature and bulk material, the silicon band gap is around 1.1 eV, and the germanium band gap is around 0.7 eV. Yet as we go to nanoparticles at around 2 nanometers, we say that the band gap of the germanium is actually larger than the band gap of the silicon. And here, then, we can use our techniques to do surface-sensitive measurements and bulk-sensitive measurements to actually extrapolate surface features and bulk features. So to give you an example that is also relevant is cadmium selenide. So the interesting thing about cadmium selenide is that depending on your synthesis protocol, it's usually encapsulated in some sort of organic, or it's in a core shell. So to probe the electronic structure of the inside, you need some sort of technique that you can put a photon in, photon out, such as fluorescence yields NEXAFS, and you can actually probe material that's buried. So in cadmium selenide, there's a number of theories about what should happen with the electronic structure that are in a little bit of conflict. And this is a really nice use of NEXAFS. So if we just look at this as is, we say, well, OK, maybe not much is happening. So we're going from bulk cadmium selenide, 3 nanometers, 2 nanometers, to one of the smaller clusters. Now we're doing from the cadmium L edge, and we know the cadmium L edge is measuring both S and D-type states. So we do a calculation of the densities of states, what should happen in the cadmium selenide, and we see that at the bottom of the conduction band, it should be primarily S-type states, whereas at the higher up in the conduction band, it's primarily P-D-type states. So if we separate that, we find that there's actually a foot at the bottom of the conduction band that we see in our NEXAFS that actually moves as a function of size that is associated with the S type of states in the cadmium selenide. And that's what's at the bottom of the conduction band in these nanoparticles. So we find that the S states actually move, but the PD states don't move. So this is actually quite interesting, as you increase in particle size, the conduction band is shifting, and then it comes to a value, and it doesn't shift anymore, because now the S states have shifted up to match with the P and D states. So here, X-ray absorption is a real winner, because we can separate the partial densities of states and actually see what's happening as a function of particle size. So perhaps that makes it a little bit clearer just to see the edges. So later this semester, I guess, you're going to have Joe Storer give talks on magnetic materials. So what I'd like to do is show you one other component here. Now, we've talked about that the X-rays have angular momentum selection rules, but there's also spin selection rules associated with this. So if you bring in circularly polarized light, you can either bring up a certain spin state in preference to another spin state. So here you can actually get NEXAFS to probe the magnetic moment in materials. So you bring in one helicity, it'll bring a spin state that's down, and in the other helicity, we'll take a spin state that's up and promote it into the empty states. So if we look at something like an iron edge, and if we take it in one spin direction or another spin direction, you can see that the L3 and L2 edge are changing. And from these changes, you can actually get information about the magnetic moment in these materials. So there's other techniques for extracting magnetic moments from materials, but the useful thing here is, again, it's element specific. So if you have a mixed state of, let's say, iron and cobalt and nickel, and you want to know the component for each one of these separate terms, here you can use the X-ray absorption techniques to actually separate iron and cobalt and nickel. And actually, I've come to my backup slides much quicker than I thought I'd be. So why don't we spend some time, and we can actually go into some detail about how the polarization dependence works in these materials. So if we look at the polarization of these materials, you can have polarization for, in this case, for the vector. This is for molecules bonded to surfaces. And you can see that you have the I term here. That's the intensity. And it's related to the theta, phi, and delta. That's basically the dot product of the electric field with the transition dipole moment. So here you have an intensity versus theta, phi, and theta, phi, and alpha in this case. So you have one intensity that you can measure in your X-ray absorption. You have three unknowns. But what you can do is in this case, you have a threefold symmetry, and a number of these terms will actually drop out, and it gives you this dot product that's at the bottom. That's I versus alpha, theta, and phi. And what you can do is you can take the different spectra here, where you're actually changing theta. So you have at 20 degrees, you have one term, and then you change your theta, keeping the one fixed, and you take the intensity difference between I at 20 and I at 30, you can actually get a value of cosine theta versus I. And this gives the theta is the difference, that's the angle of the material on the surface. So this is for a vector on a surface. And if the plane, you have the same sort of idea here, but now you have a normalization phi plane. So I think I will leave it there at the moment. I'm finished faster than I thought I'd be, and I'd open it up for any questions that you have. Yes?
Can you go back and kind of explain a little more the quadrupole transition and what exactly it is, I guess?
Where?
On your fourth slide. Here. Okay, so the
The quadrupole transition is basically this term to the 4th power. So you can, which one are we talking about here? Here? Basically, when you so I've only shown the Fermi-Golden rule for the first state, so it's hard to. I think the best is for me to show you offline, because I don't have the expansion of the terms correctly. But basically, they're I'm missing the term. It's a second order effect in your matrix elements. And sorry, I'm missing the term.
Is that somehow or other related to the overlap of the wave functions? Which,
yeah, so you can.
I mean, when you compare the dipole with the quadrupole, what's happening physically that's making this such a weaker effect?
Well, basically, it's a second order effect. So you can. It's the overlap of these two things is weaker. So the primary effect, you have good overlap between the S and P using the dipole approximation.
Steve, you had a question long ago about the angle dependence of, was it angle dependence for photo emission? If you can remember the question, this might be a good time to ask.
Well, the question was actually not, I mean, I guess it's somewhat related. Basically, could you use this technique to find your, like an indirect band gap for a given material, or perhaps, I mean, I guess because it's a surface sensitive technique, you could maybe separate surface effects out of band gap for material.
So that's a good question. If we, here, let's, so if we look at our structure for our nanoparticles, one of the interesting things here in the nanoparticle is that at these sizes that are below 3 nanometers, a lot of the atoms are now on the surface of the nanoparticle. So how do you separate perhaps a surface effect from an actual quantum confinement effect? So what you'd have to do in these type of situations is actually combine this technique with photo emission probes, where you can actually extrapolate what's the bulk component to the surface component in the photo emission. The other thing that's of interest is as you vary the particle size, you'd expect that there'd be a quantum shift, but there would also be a significant decrease if you're increasing the size of your particles of the surface component. So in these nanoparticles, we actually find that there's a clear contribution of surface in these things. These things actually have a disordered surface and a crystalline core, and that actually comes into the X-ray absorption probes. We can separate those effects out by doing the appropriate surface and bulk measurements.
So in the graph here on the left, the peak around 100 eV in the nanoclusters versus the bulk.
Yes, okay, so what you have to realize here, this is a slightly different technique, and this is an X-ray emission plot. All right, so what happens in this case is if you have an absorption, as showing here, we bring in an incident X-ray, we can kick an electron from the core level up into the unoccupied levels. With that core hole there, an electron can fall down from the valence band. in some of the cases, that electron that falls down from the valence band ejects a produces emission X-ray. If you energy resolve the emission X-rays, you can actually map out the valence band densities of states. Now, what happens there is you have a certain energy where you're exciting this process at, and the sharp peak that you're seeing in the valence band is actually that excitation energy.
I have two questions. The first is that is the quadruple transition sensitive to the polarization of the X-ray? And the second question is why in photo emission experiment the photoelectron is strictly linear to the X-ray photon you sent into the sample? I mean, why it's proportional to the X-ray you come into the sample?
Okay, in the photo emission process, you have an X-ray coming in. It kicks out an electron out of the core hole, and the X-ray that comes out, you measure the kinetic energy of that ejected electron. So what you're doing in the photo emission process is you're actually mapping out the field states. So you have a X-ray energy h nu, and that's going to be related to, actually, why don't we? So you have h nu coming in. So and that's going to be related to the binding energy of this level. Plus the kinetic energy of this ejected electron. The binding energy is measured with respect to the Fermi level. So you want to get up to the vacuum level for this to be relayed, for the electron to actually get out of the sample. So you have a term, a work function term also. So in this case, we're measuring the filled states, the ones that have the electrons in. We bring in an X-ray, kick out the electron. You can measure the kinetic energy of the ejected electron and determine what the binding energy levels are. Now, I'm not sure what your question was here.
The question is, during the lecture, you said that there's two ways to get X-ray absorption. One is detecting the transmission. The other way is detecting the photoelectron.
Okay, I see where the question is.
I'm questioning why the number of the photoelectron is proportional to the absorption.
Okay, I see. All right, so photo emission process. So in XAFS, we're kicking an electron up into the empty states. We have a core hole now here. An electron can fall down from the valence band, and to conserve momentum, an Auger electron can be ejected. This Auger electron will cause secondary electrons to also come out. So you actually get a cloud of electrons that come out with the Auger electron. So you can measure the electron yield in two ways. You can have an energy system to measure the energy of the electron, so you just measure the Auger electrons, and that's related to the core hole. But as it turns out, people have done studies where they've looked at all the secondary electrons coming out, and they've also found that the total secondary electrons that come out are also proportional to the original core hole. The original core hole is related to the absorption process.
It's a strictly linear relationship?
That is perhaps a little bit controversial, but at this point in time, people believe that it's a linear relationship. So if you measure something like the transmission and compare it to the electron yield, you get very similar X-ray absorption structure.
Another question is, I'm wondering, is in the quadruple transition, is sensitive to the polarization of the X-ray?
So I would have to defer that, because the quadrupole related of that term I'm not as familiar with, so we'd probably have to discuss that after.
I don't know if it's fair to ask you this question, but it's been lingering with me and the class, I think. So it really goes back to the very beginning, not so much from your lecture, but so suppose you have an absorption of a photon, and now you've got an empty ground state, let's say, an empty a hole in the ground state. And now the question is, for high Z or low Z, why you would see a characteristic or fluorescent photon thrown off in or an Auger electron. And basically we found that we didn't really understand the Auger process. We sort of have the understanding that we understand the characteristic photon being thrown off because we've been doing that since high school chemistry, and that's all we talked about then. But now as we get into the material science, when we learn more about the Auger process, the question is, why is that happening physically? And you mentioned about conservation of momentum, so it just sort of it popped up. Oh, maybe there's some more information here. So anything you could tell us on that would be appreciated.
Comparing, let's make sure I get the question right. You want me to compare the fluorescence yield to the electron yield, and why is that different?
Well, give us the physical model. We've seen the curve, so we know for low Z you get one, and for high Z you're more likely to get the other, but we don't really understand why when there's a vacancy, let's say a K-shell vacancy, why is an Auger, what drives an Auger process? Why would that be more important than the emission of a photon?
Well, so it is true that for the higher Z materials, the higher Z materials for K edge and L edge, the fluorescence yield is actually quite a bit higher. And I believe that in one respect is that at the lower energies, it's just, and this is perhaps a cop-out answer, is just more favorable for the Auger process to happen. I think to one degree you have so many electrons in the delocalized valence band that's close that the Auger electron coming from a valence band has a tendency to knock out more secondaries and cause a cascade process, quenching core holes easier. Now that's a bit wishy-washy, but
So I think I got that, but let's say you were looking at nitrogen or something like that, and you had a K-shell vacancy. There the likelihood would be an Auger electron. And our question is really, why is the Auger process happening? What process is going on amongst all those remaining electrons that's forcing them to kick out one?
Well, in the simple terms, obviously, it's just conservation of momentum, because you've got an electron that's dropping down from a state that's bound into another state, that your system has got to conserve momentum, and what it does to conserve momentum is eject out an electron.
I see. Okay, so that helps, actually. So there's an electron dropping down in some radial direction, and by this simple model, there's a radial ejection of some other electron.
Sure.
I see.
Now,
it's more than we were thinking, at least for myself.
That doesn't explain, per se, why your original question is why lighter Z, the Auger process, dominates. Whereas for higher Z, especially for K and L, you get increased fluorescence yield.
So an associated question, you also said that there are secondary electrons emitted upon the emission of an Auger electron.
Yes.
Is there some sort of momentum conservation that has to occur in the injection of the secondary electrons then as well?
Well, the secondary electrons are a bit trickier because what's happening there is you start getting inelastic processes. And inelastic processes, all bets are kind of off.
Well, an unprofessional comment maybe that I wish wasn't over the internet, but but it may be that in the higher Z case, the nucleus is playing such a strong role, whereas in the lower Z case, the coulombic interaction amongst the various electrons might just be a stronger effect.
Possible.
Okay, well, thanks for trying that one. Anyway, we have momentum now to think about. Okay, any other questions? No. Okay, let's, again,
Thank you very much.